everybody, and welcome to our webcast, and thank you for spending some of your valuable time with us. This webcast is presented by Logix Insulated Concrete Forms and is sponsored by ICF ProLink, which is an online database that matches incoming ICF leads with ICF experienced installers, architects, designers, and engineers. My name is Andy Lennox. I'm the Vice President Marketing Solutions at Logix Insulated Concrete Forms. That's my day job. In addition, I've got the privilege to serve as the chair of the ICF Manufacturers Association. This association has the members are the manufacturer members combined to have perhaps 80 to 90% of the ICF market in North America. So the ICFMA really is the voice of the ICF industry in North America. The ICFMA does many things to enhance the position of ICFs in North America. And one very important thing that it's done recently was to publish the thermal test that's going to be the subject of today's webcast. This thermal test was published last week. Over the last week and a half, our Logix ICF technical staffs had the opportunity to review it and understand the findings and to analyze them. And so we're pleased today to introduce Francis Roma, our technical director at Logix ICF. And he's going to present and offer his insights into these very important test findings so that hopefully after this webcast, you're going to be in a better position to understand the results and the implications of these test findings. We have a lot of people on this webcast, so we've got everyone muted so that everyone can listen and hear things without a lot of noise. However, everyone's got the opportunity to ask questions on their on the keypad. If you do have questions, we will note them and we'll try to get to as many questions as we can in this webcast. Any questions we don't get to, we'll get to you afterwards. And we will be posting this webcast online for future viewing. So without any further ado, over to you, Francis.
All right, thanks, Andy. Thanks again, everyone, for being with us for this webcast. We are calling Thermal Performance Test of ICF versus Stud Wall. So this presentation will probably take about 30 to 35 minutes, and then, like Andy said, we'll do a Q&A towards the end, and I'll try my best to answer all the questions. So let's get started here. So we're going to talk about the latest research that was conducted on ICFs. We're going to talk about the results and what we learned from the test data. So this research was commissioned by the ICFMA, the Insulating Concrete Forms Manufacturers Association. So it was industry-led effort. The testing was done independently by CLEB Laboratory out in Quebec, Canada, and they are a certified agency that specializes in building envelope testing and research. So CLEB carries a number of accreditations and approvals. They have SCC, AAMA, NFRC accreditations, and they also have Florida Building Code and CCMC approvals. So what was the purpose of the research? Basically, it was to determine how calculated or book-listed R values of a 2x6 framed wall and an ICF wall compared to the tested or actual R values. To do this, it was based on a standard test of ASTM C1363, which is basically your industry standard for testing large-scale wall assemblies for thermal performance. So this test measures the R value of the complete wall assembly, not just the insulation material itself, because every component in your wall assembly contributes to the total R value. And so this test will provide more accurate and realistic R values compared to perceived R values of wall assemblies. So what we expected from the research to find was that the frame walls would have a lower tested R value compared to its perceived R value, and the ICF would have either same or better R values compared to its perceived R values. And we expect that because there's no thermal bridging in the ICF, it's continuous insulation with a continuous air barrier and the whole bit. But we did learn more. The testing provided more important information, and it confirms what other independent studies have shown about ICFs. and that is that the thermal mass, the continuous insulation, and the air tightness of ICFs creates a highly energy efficient wall system, especially when you compare it to stud or framed walls. So before we get into the results and the data, it's important to understand what steady state and unsteady state conditions are. Because at steady state conditions, that is when the R value is actually measured. But at unsteady state conditions, ICFs have quite a significant effect compared to other wall systems, and we'll get into that later on. But what I'll do in order to explain steady state, I got to give you a bit of background on the test setup and what was actually measured. So I'll try not to get too technical. I just want to give you the basic concept of steady state if you don't know what it is already. So what I've got here is a simplified schematic of the test chamber. And in the test chamber, they can control the climate conditions in there. So in the test chamber, they have a test wall, which is 8 feet by 8 feet. On one side of the test wall, it's exposed to a constant temperature of 21 degrees Celsius to mimic indoor temperatures. On the other side of the test wall, it's exposed to a constant temperature of minus 35 degrees. And that's to mimic extreme cold conditions. So the test setup will basically mimic extreme winter conditions. So the indoor and outdoor temperatures, once they reach these temperatures of 21 and minus 35 degrees Celsius, that's basically when they start the test. So what's going to happen during the test is heat flows from a warmer place to a colder place. So heat's going to want to travel through the wall system. And at some point, there's going to be enough heat transfer that the indoor temperature is going to drop. So it's going to experience heat loss. When that happens, to maintain 21 degrees Celsius, you have to add heat. And as you lose more heat in the chamber, you're going to have to add more power to keep it at 21 degrees Celsius. At some point, the power you're adding will remain constant. It's not going to change over time, so it's steady. At that state, the system is considered in steady state conditions because everything in the system remains constant. There's no change. And it's at steady state conditions that the R value is actually calculated for the wall assembly. So at steady state conditions, we have everything constant, the indoor, outdoor temperature, the indoor, outdoor temperatures, the heat transfer through the wall, the energy being supplied is constant. And basically, the energy being used in the system is equaling the energy being lost in the system. And that's basically what steady state is. Try to come up with a more simpler analogy because to me, it sounds confusing when I explain it. So if you think of a cup full of water, it's in steady state conditions. The water level doesn't change. It stays where it is. But as soon as you poke holes in the cup, the water will flow out. And the rate of flow out of the cup is going to change as water level drops. If you want to maintain the water level back to the top of the cup, you have to add water to it. And that rate of flow of water that you're adding is also going to change until it reaches the top of the cup. So everything in this system is changing, the water level, the flow in and the flow out. So this system is in unsteady state conditions. As soon as the water level reaches the top of the cup, the amount of water you're adding in can remain stable because it's going to equal the amount of water exiting the cup. So everything in the system is stable. The flow in equals the flow out, and because of that, the water level stays at the top of the cup. So this system is in steady state conditions. And that's basically what the same concept for the test chamber. You're losing heat through the wall. You've got to add more heat to the chamber to maintain 21 degrees Celsius. At some point, the amount of heat you're adding or power will remain constant, and that's steady state. So at steady state, this is the formula that they use. The power supplied will be what is being supplied at steady state conditions. If you look at the formula, it's got the area of the wall, which is constant, and the temperature on either side of the wall remains constant throughout the test. The only thing that changes is the power being supplied. So in unsteady state conditions, the power increases until you reach steady state. So at steady state, that is when they calculate the R value. So let's move on. Hopefully that explains what steady state conditions are in unsteady state. So we'll look at the walls that were actually tested for the study. Just as a side note, this is a first test in a series of wall assembly comparisons that will be likely undertaken by the ICF MA. Additional wall assembly variations will likely be tested in the future and probably under different climate conditions. So the ICF MA had to start somewhere, and these are the walls that were chosen for this study. So let's look closer at the walls that were done. We have a 2x6 wall with an effective R value of R18. So this is the calculated R value for this wall. Values were taken out of ASHRAE, and thermal bridging was considered in the R value calculation. So what we've got is we've got drywall, strapping, the vapor barrier, 2x6 frame wall with R20 cavity insulation. We have the OSB, house wrap, strapping again, and then the vinyl siding. So the vinyl siding side was the side that was exposed to the cold chamber in the test setup. This wall assembly meets climate zones 1 to 5 for above grade in the IRC, and meets climate zones for above grade in the National Building Code. It meets all climate zones in Canada. For the ICF test wall, it had an effective R value of R24, and the assembly included drywall, then the ICF, which was 2 5/8 inch EPS form on both sides with 6-inch concrete, and 10M rebar at 18 inches horizontal and 16 inches vertical. This says 8 inches, but it should actually say 6 inches. So it also had strapping and then the vinyl siding. And again, the vinyl siding side was exposed to the cold chamber in the test setup. This wall assembly met all climate zones for above grade in both the IRC and the National Building Code. A couple things that you may have noticed in this test wall assembly. The frame wall has strapping on both sides of the wall. It's probably not something you'll do in the field, but for this test setup, it doesn't actually reduce the thermal performance of this frame wall. It will actually improve the thermal performance. So if anything, it's adding to the performance of this wall assembly. The other thing that you may have noticed if you've gone through the test report is the frame wall does include an opening, a window opening, and it's filled with cavity insulation as well. Basically, there's 2 reasons why that was done. Number one is around the windows, around openings is where you get most of your thermal bridging because there's more framing around there. And secondly, frame walls take about 20 to 25% of the total wall area. If you're using advanced framing methods, then it's typically around 20%. This frame wall for the test setup takes 20% of the total wall area. So it is reflective of what's actually done on site. For the ICF wall, we have strapping as well. And again, you may typically not use strapping, but it doesn't make much difference in the overall effective R value of the ICF wall because the strapping isn't continuous. It's only adding about an R.4 to the total R value of this wall assembly. So again, we're testing these walls to see if the perceived R values are going to equal its tested or actual R values. So let's see what the results showed. So just as a reminder, tested R values are taken at steady state conditions. So at steady state conditions, the frame wall got R15.2 and the ICF wall got 24.1. The energy required to maintain it at steady state was 126 watts versus 78 watts. The time to reach steady state took 60 hours versus 324 hours for the ICF wall. And basically what this means is that the frame wall remained in unsteady state for 60 hours, and the ICF wall remained in unsteady state for 324 hours. Okay, so let's look into that a little further. What does that all mean? Basically, with the frame wall, the tested R value is actually less than the perceived R value. And the tested R value for the ICF wall is actually equal to the perceived R value. So basically, out in the field, if you have a frame wall, chances are that the actual R value of that frame wall is going to be less than what it actually is perceived to be. With the ICF wall, the actual R value is going to be the same for your wall assembly. So for ICF, the R value is actually more reliable than it is for frame wall. And that has a large part to do with the fact that ICF doesn't have any thermal bridging, and it's an airtight system with continuous insulation. So you're not going to get the type of losses that you would with the frame wall. And so this test does confirm what we suspected for the most part, was that the actual R value of a frame wall will likely be less than its perceived R value. The frame test wall uses 60% more energy to reach steady state conditions. So it's pretty obvious that the frame wall is going to use up more energy than the ICF wall. But let's look at that a little deeper. So if we look at the charts from the test report, there's a chart for thermal resistance over time, and there's a chart for power supplied over time as well. For this chart, if you take a look, the frame wall in yellow, the amount of power it's using increases at a much faster rate than it does for the ICF wall. And that's because the frame wall is experiencing heat loss at a faster rate. So it's going to reach steady state much sooner. If we take a look, the steady state is reached at 126 watts in 68 hours. If this wall were allowed to continue at steady state, by the time it reached the ICF reaching steady state, the frame wall would have taken an extra 149% more energy to reach steady state. So basically, if the frame wall was allowed to continue at steady state until the ICF reached steady state, it would have used 149% more energy. With ICF walls, it remains in unsteady state 5 times longer than framed walls. So for the ICF, it is basically in unsteady state for 13.5 days, and the frame wall was in unsteady state for 2.5 days. Let's go back to the chart and take a closer look here, because the chart does tell us a lot, give us a lot of information. If you take a look, steady state is reached at 60 days for the frame wall. And for the ICF wall, it's at 324 days. And at that time, it uses about 78 watts of energy, and the frame wall uses about 126 watts. Before it reaches steady state, both walls are in unsteady state. That's why the power being supplied is changing over time. But as you can see, before it reaches steady state, the power being supplied is actually less than the power required at steady state. If we look at the chart with thermal resistance over time, you'll notice that the walls start off with a higher R value for the wall assembly, and it gradually decreases until it hits steady state again. So at steady state for the 2x6 wall, it has an R value of R15, and it took 60 hours to get there. For the ICF, it has an R value of R24, and it took 324 days to get, or 24 hours to get there. But as you can see from the chart, before it reaches steady state, the thermal resistance of both walls are actually higher than it is at steady state. So at steady state conditions, wall assemblies perform at a higher R value and uses less energy before it reaches steady state. What's significant about that with ICF is it stays in unsteady state 5 times longer. So it's using it has a higher R value and using less energy 5 times longer than the framed wall is. And this is significant, even for CLEB. They have noted that out of all the wall assemblies they've tested using this test standard, they've never seen any other wall take so long to reach steady state other than ICF walls. And that has in large part to do with the fact that the thermal mass properties in our ICF walls are playing a great role in achieving this. So another thing to take away from this is that the ICFs may take more than 324 hours to reach steady state. So let's look at that chart again. You'll note this for the ICF wall here. It's taking 324 hours or 13.5 days to reach steady state. And that's pretty impressive given the fact that this wall is consistently exposed to minus 35 degrees temperatures on the exterior. So even with those temperatures, it's taking almost 2 weeks to reach steady state. But in reality, your walls are not likely to face these type of extreme conditions. In the winter, you're still going to have temperature swings between night and day, which will affect the rate of heat transfer through your wall. So it's very likely that during winter conditions, your ICF wall is going to stay in steady state much longer than 324 days. And same thing with the frame wall here. It'll probably stay in unsteady state more than 60 hours, but it will reach steady state much faster than it will with ICFs. And in this chart, it shows it's going to do it 5 times. The ICF stays 5 times longer in that condition. The ICF wall did not require power until about 48 hours after testing. So let's go back to the thermal resistance versus time chart here. Actually, let's go to the power over time chart. So what's happening at the start of the test, again, the frame wall pretty much immediately starts using power right away to maintain the heat in the chambers. That means that the frame wall is experiencing heat loss right away. If you look at the ICF wall, it doesn't start using power until almost about 48 hours after the testing starts. And again, that's pretty impressive given the fact that this ICF wall is exposed to a consistent minus 35 degrees Celsius temperature. So what this wall is telling us is basically that there's a 2-day thermal lag in this ICF wall test. And if you look at real world conditions, it's unlikely your wall is going to face these type of extreme conditions. So it's likely that most ICF walls out in the field are going to have a much longer thermal lag than 2 days. One last note is that the ICF wall tested for this research actually has thinner panels than Logix. So the results are somewhat understated, but overall, it really doesn't matter because the results do confirm what most of us have already known, and that is that the thermal mass properties of an ICF wall has a significant role in the energy efficiency of ICF walls. So what's the next steps? I briefly mentioned that the ICFMA may be looking at more wall assemblies to test and possibly at different climate conditions. Ideally, and I'm talking long term, there needs to be a way to somehow quantify the properties of ICFs or wall assemblies during unsteady state conditions, because it's not just about the R value at steady state conditions anymore. It's about how well ICFs perform during unsteady state conditions. And again, that has to do a lot with the thermal mass properties of ICFs. So a small scale standard test that normalizes the properties of unsteady state conditions of wall assemblies that can be used for energy ratings or evaluations and get accepted by code is, ideally, I'd love to see that, because really that plays a big part in the energy efficiency of the walls. So hopefully this report and the results that I presented and the interpretation of the data gave you more insight into how well the ICFs performed. And again, it's not just about the R values anymore. It's really about how it performs in unsteady state conditions and the thermal mass contributions that ICFs provide to this. So with that, I think what I'll do is I'll hand it back to Andy, and we'll open up the floor to more questions. And if there's anything that anyone wants me to clarify during this presentation, I'm happy to do that too. Or if you want, go ahead.
Oh, okay. Well, thank you very much, Francis. We have a couple of questions that have, one question actually, and a comment. I think someone was having a little trouble with the sound on their end. I think Josh had mentioned that he was having trouble on the sound, and we apologize for that. It's likely though at your end, Josh, on the connection, because the sound was pretty good from what I could tell at our end. So hopefully it wasn't for everybody. And Josh, we have recorded this webcast, and we will post it so you can view it at a later time if you've missed anything. Feel free to send any questions that you want. We only have really one question, Francis, at this point, and it was from Sarah. And Sarah just wanted to get an idea of the cost of an ICF wall versus a wood frame wall, which is a question we're asked often, and it's a very good question. Sarah, we can't really go into that in too much detail here. Roughly, I can tell you, and it really dramatically varies from region to region, and the cost of wood and the cost of concrete and all that kind of stuff. But it's likely in the area that an ICF wall that you would have seen in this test would carry a cost premium of somewhere from $6 to $8 or $9 per square foot of wall area versus a wood frame wall. And you can see how that fits into and there's ways to analyze it to see how that fits into the overall cost of the house. Typically, an ICF built home will carry an overall premium from the overall build budget of the house, something in the neighborhood of 5 or 6%. But Sarah, we have a webpage on logixicf.com that talks exactly about that cost comparison, and I'll send that to you by email afterwards. So Francis, I think that's the only question that we had. It looks like
okay.
Your explanation completely cleared things up, which is oh wait, no, okay. So we've got a question here from Doug McKenzie, and has there been testing? Has there been testing to compare with SIPs? Which is a really great question, and the answer is, Doug, no. This is the first test of this nature, of the hotbox test that we've done, that the ICF industry has undertaken, and we picked the 2x6 wall to compare against, as that is the predominantly the wall that's the most popular alternative out there to ICF. SIPs is, you know what? I think it's a great question, and we'll certainly, when we're looking at which wall assemblies that we're going to be comparing ICF to in the future, I think it would make great sense to compare against a SIPs wall. So the answer is no, but it's on the list. Francis, your thoughts?
I would be interested to see how that performs, because SIPs do offer really high R values, and but this test does look more closely now at the unsteady state conditions. So what happens before you reach those R values? And with the thermal mass of ICFs, it'd be interesting to compare it to how well SIPs perform during unsteady state conditions too. Like, do they last as long because they don't have thermal mass properties, just, the thick foam insulation? So it'd be interesting to see how it works under those conditions.
Okay. We have a question from Eric Larson. Eric asks, why does the R value and energy consumption used by ICF tend to jump up and down more so than the stick frame wall?
Well, let's look at the chart. Could be a number of reasons. The only thing I can think of is the power being supplied is decreasing and increasing, and that could mean that that the heat transfer through the wall is coming in and out of the chamber. So when that's happening, you're either increasing the power or decreasing the power. There could be other variables involved, but to me, that's what the chart is showing.
Okay, that's actually a great question by Eric. We have another question. This is off the topic of the thermal test, but Mark is asking, can you talk about ICF being a sound barrier and its effectiveness in reducing sound transfer?
Well, ICFs are actually well known for dampening sound transmission through their wall systems. You know, they're obviously used a lot for theater walls, but in terms of specific R values, it really depends on what's on there, how thick the ICF is, and how thick the wall is, and all the components you put on it. But in general sense, they basically have high R values.
Sound attenuation.
Right.
Yeah.
Yeah. So if we're comparing it to stud frame walls, for example, obviously it's not going to be as good unless you put a lot of layers on that stud frame wall, because you are going to get sound transfer through the studs itself. ICF walls, it doesn't really have that effect. We do have ties, but I don't think it has a great effect as it would for a stud frame wall.
Okay. Nathan asks, I'm sorry. Wait, I'm getting myself lost here. So, do we have a comparison at this point to the effective R value of an ICF wall versus a conventional concrete foundation? And no, we don't. Once again, it's along the lines. I mean, it's obvious that we've kind of tapped a nerve here with this test, and it does brings it shines the light on a lot of underlying building science, and certainly you can see the difference between ICF and framed. And now everyone's starting to say, well, versus SIPs and versus concrete walls. You're right. We have to start doing this to understand how other walls assemblies operate and function versus an ICF. So the answer is no, but it's on the list. Now, Francis, I'll defer to you to any other comments there.
I didn't quite catch it, but I'm assuming you're wondering if there's a comparison with just exposed concrete, conventional concrete. Was that?
Yeah, conventional concrete basements. Yeah.
Yeah, it would be interesting to find out, because with exposed concrete and foundation walls, basically you don't have the insulation that ICFs have. So the concrete in the basement wall, whether it's exposed or not, it's going to have thermal mass properties. But the difference with the ICFs is with that thermal mass, the concrete is going to want to absorb that heat and then eventually release it. But because we have more than 2 inches thick of EPS on both sides of the concrete, any heat that the concrete wants to absorb, it's got to make its way through over 2 inches of EPS insulation. And then when it releases it, it still has to get through another 2 3/4 inches of EPS insulation. So it does slow down, we think, the rate of heat transfer through the wall. And you don't get that with, exposed concrete or foundation wall without any insulation. So it'd be nice to see in a comparison and see how they actually perform.
Okay. All right. Another question, and all right. So we have a gentleman here who missed the beginning of the presentation and does have a question. And Tyler has asked, were the ICF walls poured or still hollow when the test was done? Tyler feels that R24 seems low for poured walls. Okay, and that kind of calls to the whole point of the test in steady and unsteady state. So I don't know how in depth you want to go on this, Francis. Tyler, you may want to view the recorded presentation at a later time, and you'll get full context. But Francis, I'll throw it over to you.
It was tested with concrete in there, 6 inches of concrete, and it was allowed to cure for 28 days as well. But the R24 value, I think it's pretty common for most ICFs because that is basically just the R value of the wall assembly. But if you're wondering why it's so low, I don't know. I think that's what they typically are. But when you consider thermal mass, obviously there's going to be a much higher performance in terms of energy efficiency.
Which is what this test indicated and proved. So
right.
Okay. All right. So now Larry asks, what were the initial temperature conditions in the chamber?
So how it worked was the indoor and outdoor chambers, before the test started, I don't know the specific details, but before the test started, they had to maintain 21 degrees and minus 35 degrees Celsius. As soon as the test chamber was maintaining those temperatures, the test started. So there may have been some heat loss already happening just before the test started, but that's essentially how it begins. They make sure that there's tons of monitoring going on, and they make sure that they start recording once they're able to maintain the temperatures within the chambers.
Okay. All right.
So yeah.
I'm sorry, Francis, carry on.
Oh, no, I was just going to say, so they don't bring it up to that temperature during the test. They're already at that temperature when the test starts.
Okay. All right. Another question. The American IECC codes consider component R values. How can the CLEB results be used for the U.S. Market, and given how the American IECC codes consider R value?
Yeah, that was part of my point about trying to come up with a standard that normalizes all this, because I believe the codes in the U.S., it's not really based on the total wall assembly. It's just the R value of the insulation itself, and you can correct me on that if I'm wrong. So to sell this down in the States, or even in Canada, it's going to be difficult because everything is based on R value. It doesn't consider what happens during steady state conditions. So, you know, ideally at some point, it would be great if they could somehow measure and quantify and compare wall assemblies on unsteady state conditions rather than just at steady state conditions. And, you know, hopefully that made sense and answered your question. But, you know, it's a challenge. It's going to be a challenge.
Well, the point is, though, there's great value to this test because, I mean, if you've been in the ICF business for any period of time, from everything that you hear, it's a great business to be in because virtually everybody that lives in an ICF building is happy, and the amount of complaints that you get about the end product is almost negligible, really, and people, you know, often say, you know, my energy savings are far out of context to what the stated R value of a ICF wall would be. You know, it's your R24 versus an R20 wall. That's a little bit of a difference, but the energy savings are so much higher. But that's what this test showed. It's not about R value. It's about the actual thermal performance that occurs at unsteady state, which is almost a permanent condition for an ICF wall. We've got a question here. What kind of performance increase would you expect? And we're going to get hypothetical here, Francis, because we're getting into hypothetical. What would you expect from an ICF 6-inch wall to an 8-inch form? So how do you think these numbers would change if we tested an 8-inch ICF form?
You know, it's hard to say because you can't do interpolation. If you look at the chart, it's not linear. All I can tell you is that with an 8-inch wall, you're going to have more thermal mass with an 8-inch wall versus a 6-inch wall. So you would expect that it would stay in unsteady state even longer. And your thermal lag, in this case, was 2 days. It'll probably be longer than 2 days as well. So the thicker your concrete, the more thermal mass properties you're going to have. But specifically how much more, it's hard to say unless you do the testing.
Yeah, and that question was asked by Matt, and Matt has this feeling that he sees a lot more 8-inch than 6-inch out there, and I'd say yes, 8-inch is very common, Matt. And once again, it's very regional. Certainly below grade, there's an awful lot of 8-inch, a lot of 6-inch as well, but an awful lot of 8-inch. But this test really wasn't about below grade. This was about above grade, comparing an ICF wall versus a wood frame wall, and wood frame walls are really only above grade. So now we're above grade. I'd say that 6-inch concrete core is probably the most common ICF wall in my experience that you get above grade, certainly in residential. Now you get into mid-rise buildings and such, and taller buildings, you can certainly get into 8-inch. But no, I think a 6-inch wall is quite representative from a residential above grade wall. Would you agree with that, Francis?
Yeah, I'd agree with that. Yeah.
Yeah. All right, I've got a question here, and I'm going to read it as I'm going, and the gentleman is warning me it's kind of off topic. He's talking about, okay, so Jason says he's about to do, or he wants to do, a large bank of multi-fold doors. And this is right off the thermal performance question, Francis. It's getting into your into structural engineering. How large of a span can we create with ICF?
Height-wise or lengthwise?
Lengthwise.
I
believe.
Well, lengthwise. Okay, so length.
Yeah.
It depends on the codes. Basically, there's two ways of doing this. In theory, you could go as long as you want, depending on the wall height. But because you have wind conditions and other loading conditions on that wall, you may have to put, intermittent supports for that wall. But it depends on the thickness. That's a tough question because it can change and vary. It's probably easier for me to answer that question if I saw your plans and what your loading conditions could be, but typically they can span pretty far. You go 100 feet probably without putting any additional supports in it. Again, it all depends on the design conditions.
Okay. Now, all right. Okay, Francis, I'm just trying to read the question here, and this is actually a very important question. It calls to the heart of this test. And here it is. Previous studies have indicated an R44 equivalent R value for ICS. Does this study clarify this or eliminate this finding? I think the study really is positive. Well, I think the study is very positive for ICF. I mean, at steady state, ICF is the ICF wall in this study test was R24. But prior to reaching steady state, the ICF wall acted well above the R24 level. And so that's where you're getting the notion from, perceived R value to effective R value. And so I think these walls, this test result, in fact, would likely validate something of that finding. And Francis, I'll send it over to you.
Yeah, I think I know which study that was, and theirs was based on testing and evaluation using different methods. And yeah, it's like I said in the presentation, a lot of these studies for ICS show that ICS is really energy efficient. And that's just one other study that backs it up. I can't remember how they quantified an R44, but it wasn't based on this test standard that we're doing here. It was a more elaborate test, a more elaborate test study from what I recall.
And quite to note, I mean, on the chart that we're seeing here, around the 130-hour mark, the ICF wall started to act at R44. Prior to that, the first 100 hours of this test, it was operating well in excess of R44, and then operated gradually from R44 back to down to its perceived value of R24. So this is these are outstanding results for the ICF wall. Were the ICF walls poured for this test? Taylor asked this, and the answer is yes.
Yeah.
Okay. What is your test chamber made from? And what? Okay. We have what is your test chamber made of? What is underneath and top of it? And does it sit on bare ground?
Okay. Well, the test chamber is actually a really sophisticated piece of apparatus. It has to control the climate conditions within it. So it's basically a box, and the entire, all 6 sides of it is fully insulated. And I don't know, some may be more insulated than others, but there's different types of models out there. There's actually companies and manufacturers that make these test chambers specific for this testing. So I couldn't tell you what exactly it's made from. It can vary, but the insulation on these boxes is quite high to maintain the climate conditions within it.
Okay. John asks, did this hot box test take into account the air tightness of the wall assemblies?
It does. So basically, during the test, it wasn't just introducing heat into the system. It was convection, conduction, and radiant heat being introduced. So convection and conduction, they had fans blowing in the chambers to mimic more realistic conditions, especially on the exterior. So with ICF, it's naturally an air barrier because of the concrete in there. With the frame wall that was actually tested, I guess you could see it in the charts how fast the power had to be supplied to maintain it. But you know, for the frame wall, it was actually sealed as well with the vapor barrier to maintain a tighter air system for it. But with the ICF, yeah, air in the general sense, air barrier was considered, or the air tightness, just because that ICFs are inherently airtight to begin with.
David asks, and we're going to have to cut the questions off at some point, but these are good questions. David asks, what's the RValue? What's the thickness of Logix ICF panels, and what is the RValue of Logix ICF panels? So the ICF that was tested in this test, I believe the thickness of their panels, and there's an interior panel, exterior panel. I think it was 2 5/8. Francis?
That's right. That's right.
Okay. And a Logix panel would be is 2 3/4 inches. So each Logix panel is slightly thicker. So the RValue of this particular ICF wall assembly was R24. Francis, what do you have on the top of your head what a comparable wall assembly with Logix ICF Pro would be?
With the exact same assembly as the test, I couldn't tell you offhand, but we're probably hitting R25 with that wall assembly.
Okay.
Just because our values are thicker.
Yeah, slightly more. Slightly more. This wall assembly was R24. Logix would be R25 or something like that. Can you get copies of the slides? Yes, we're going to send out some slides, and we're going to post this presentation online. Okay. We did. Okay. 8 inches is very typical below grade. We did above grade 4 inch typically. Would be interested in that comparison. So Josh is saying, hey, you know, should we not test 4 inch ICF walls? And you know, we should test 4 inch ICF walls. We should test 8 inch ICF walls. And it's, I think, what the direction we're getting from the crowd is versus conventional concrete walls versus SIPs. So
yeah,
this
I
is,
agree. Totally agree.
Yeah, this is great feedback that I'll take to the ICFMA, and when we look to what we're going to be doing. Okay, so I think we're going to have to cut it off here. There may be a couple of other questions that we haven't got to, but I think we're going to have to cut it off here in the interest of time. Any questions that you've left, they are recorded. We will get back and we will answer them to you one-on-one. In addition, when you get a follow-up email from this from us for this webcast, you'll have an opportunity to ask even more questions. Whatever questions you have, we will answer them. I want to thank Francis very much for offering his expertise here. This was a complicated webcast, a lot to get out, and thanks very much, Francis, and thanks very much for everybody. Thanks very much for everybody that took the time to be with us today. From the number of people on and from the number of questions, there's obviously, this is a hot topic, and it was great to engage with everybody to get the story out. So let's keep the conversation going. Thank you for attending, and have a great day. Thank you.
Thanks,
everyone.
everyone.
This is the end of the webcast. Thank you.